Okay, so we go for our tutorial question number 14. Not 14, number 15. Chapter 2, tutorial question or your handout number 15. Okay, now we try the similar solving strategy for this question. So if you look at the screen, you will have 3 elements. So element 1 connecting point 1 to point 2, element 2, 1 to 3, element 3 connecting point 1 to 4, and the axis now back to the normal. So x is to the right, y is vertical. We have some external force at point 1, which is 25 kilonewton vertical going down. So again, compared to the axis, later your force at point 1, you get a negative sign there because it's going down. And K stiffness matrix for spring is given. So in this case, it's a combination of bar and spring, right? So again, you need to recall what is bar, what is spring. So we have an equation for bar and spring here. What else? The E is given in this question. E is 210 gigapascal. Area is 5, 10 power negative 4 meter square. Bar 1 has a length of 5 meter. So this is 5 meter. Bar 2 have a length of 10 meter. Spring, you have stiffness matrix here. So we need to find the displacement, yeah. So in this case, the question didn't say want to solve what, but normally you still back to the general equation. If you really don't know what the question asks, you can estimate, yeah. So in this question, of course your task question or final exam you won't see the question like this, yeah. So again, still back to your fundamental or governing equation. F equal to KD. Again, curly, square bracket and curly. So here, you know that you need to find force, you need to find stiffness matrix, you need to find the displacement. So general step is you start with the stiffness matrix, followed by finding displacement. Okay, before displacement, you have boundary condition apply to the equation here. Then you solve for displacement. Then you solve for force here. So it's quite direct. Yeah? Okay. Then for bar, you use because bar have modulus Young and strain, mechanical property. So your force equal to AE divided by L times your displacement. Yeah. So, and then for spring, quite direct. So spring, you use Hooke's law equal to Kx, right? Okay, before we move on, so angle is 45 here. Okay, now I'm going to ask question already. I'll ask question about theta. Theta for element 1, what is the value? Theta for element 2, what is the value? Theta for element 3, what is the value? Okay, I'm going to ask Katana. You answer for the first one. Lai, you answer for the second one. Singi, you answer for the third one. Okay, Katana, what is the angle for element 1?
35.
Again, your answer?
135.
135. So correct, 135. Lai, you understand why 135? Lai, are you there?
Oh, yeah.
How you get 135 for element 1? How you get 135 for element 1? Can you explain?
180 minus 45.
Yeah, you still get the same magnitude, but the way you explain it is the concept is a little bit incorrect. How you measure angle? You measure angle from what? From what axis to what axis? You measure angle from what? You measure angle from x prime to x or x to x prime.
H3 to H1.
No, from this diagram that I draw on the screen here. You have x and x prime. You have two axes here. The angle you measure from x prime to x or x to x prime?
S to S prime.
X to x prime. So in this case, where is your x? Here, right?
Right.
Where is your x prime? Here, right?
Yeah.
So angle is from here to here. So when you explain is from here to here, so you have 90 plus 45. Yeah, okay, you can take 100. Your answer you just now is 180 minus this one. Also correct, but a better explanation, you should explain how you measure the angle first. Yeah. All right. So okay, Lai, your answer for angle number 2, what is the answer for element 2?
180.
180, correct. Singi, what is the angle for element 3?
270.
Correct. Okay. So we have all this angle, and then you build the table for element 1, 2, 3. You find the cos, sine, cos square, blah, blah, blah. Okay. So you build the table, and then you use your calculator, punch in number, you get all this. Then you build the stiffness matrix. The steps still same, yeah? Okay. So the matrix still use the same. K equal to AE divided by L. Of course, if you see the AE over L here is for the bar, yeah? Spring, we don't have A and E, yeah? And L we don't have, yeah? So, so we already solved all the angle, right? So for element 1 is 135. You find the cos and sine, build a table, you get the answer. So for K1, A is given, E is given, the length is given. So you put in all the numbers that you pull from the table that you built. You have the cos square, cosine, negative cos square, negative cosine. So we refer to the governing equation on the top of the screen here. Then you calculate accordingly. So it is recommended you build a table and then you import accordingly, and you will save a lot of time. Okay, you build the first stiffness matrix for element 1. You repeat for the, okay, so this is just an illustration on getting a simple equation where we have 1 and 0. So in this case, we have 1 and negative 1 in the answer. So your constant value outside here is 105 10 power negative 2. Okay, so we have this number. So you can simplify this one and this one become this one, yeah. Okay, element 2, 180, you do the same. You get stiffness matrix for element 2. Import your A, import your E, import your L, and you do the calculation here. And then you do the same, you simplify so that your matrix will get 1 and 0 and 105, 10 power negative 2. So before we proceed, again, just remind you to do some marking. So for this case, element 2 is 0.1 and 3. So label U1, V1, U3, V3. Okay, because later we want to do is superimpose into a very big matrix where we will have a 6 times 6 matrix. Yeah, so so for element 1 also same. Element 1, you have 2 point, 0.1 and 0.2. So you have U1, V1, U2, V2 here. So later you need to import into a very big matrix. Okay. Then element 3 will have 270. Sorry, there's a number missing here. It should be, there should be number 3 here. Okay. Then you do the same, but this time without the this time you will have your K instead. Yeah. So this is your Hooke's law, F equal to Kx. Yeah. So this is your K given. All right. So your K is 2000 kilonewton per meter. So if you calculate back this one, the previous one, you must put them in the same unit. So this one is in 2000 kilonewton over meter. So you write, so this whole thing is in kilonewton over meter. Okay. So the same with the previous one. So if you calculate the AE, so we take this one and time this one, you will get kilonewton over meter also. Yeah. This one cancel by this one. So you get kilonewton over meter. Yeah. So this term here is kilonewton over meter. Okay. So now we want to combine. All right. Combine all these three together. So we have three metrics there. Yeah, before we combine, we will have the boundary condition again. So from this case, point 2 was mounted to the wall with a pin. Point 3 was mounted to the wall to the pin. Point number 4 straight away inside the floor or the wall. So there's no displacement in point 2, 3, 4. So all these U2, V2, U3, V3, U4, V4, all 0. So it will reduce your equation after you build the global matrix. At the end, you know that you arrive at your F equal to KD. So for the first element, you only reduce to this equation, this matrix equation. So F1x, if you look at here, F1x, you don't have an external force here. So you put 0 for F1x here. It's a capital F, yeah? It's a capital F here, not a small f. Capital F is look at the external force. So there's no external force in x direction, but there's a y with a negative sign there. It's going down. And then you put in the AE over L here. This one is this one. Okay. Then you times the U1, V1. So you have two equations here, two unknown. So you're able to find. Let me change the color just to refresh how to do matrix. this one equal to this one times this one. Okay, so again, remember to pull in the 10 power 2, this one plus this one times this one. Then the same for the other one. So you'll get what is your U1 and V1. So again, you get a negative sign. Expect that the question sometimes will ask you to explain the direction of the movement, direction of the displacement. So in this case, you get a negative sign for point 1, negative sign for point U1 and V1. Yeah. So okay, lie. If you look at the screen here, let's say you calculate and then you get U1 equal to negative 1.7 10 power negative 3 meter. What is the direction of the displacement at point 1? Does it move up, move down, left or right?
Left.
Move to the left. Correct. The answer is correct because your x direction is to the right. You get negative. Yeah. Okay. Yeah, let's test. Singi, so what is the direction for, what mean by V1 negative 3, 10 power negative 3 meter? What does it mean? What mean to the displacement?
Moving down 3.448 times
Okay,
10 to the power.
right, correct. So this is how you solve a test question. Yeah. So when you get a negative, you need to explain what does it mean? What does the number mean? Yeah. Okay. Then for the stress, again, call back the equation for stress. Stress equal to C prime D. So if the detail is in the previous slides, go back to the previous slides if you don't understand this one. So C prime equal to this whole equation here. So you find the stress inside the element 1. So stress 1, and then you put in all the value. E is given, L is given, cosine you can find just now, and then you put in the displacement accordingly. So you already find your displacement, 0.1, 0.2, all this, and then you put inside there, you solve the equation, you find stress 1. Yeah. So for the stress experienced by element 1 will be 51.2 megapascal. And when you get a positive sign, it means that if you have a bar like that, again, if you have positive sign stress, it means you have a tensile stress. It means you're pulling at both ends. If you get a negative sign, it means you have a compress. You have a negative, means you have a compressive stress, or you have the object was being compressed, not compressible, compressed stress. Yeah? Okay, this is how you solve for stress. Do it for element 2, repeat the same process again. So yeah, you substitute the E, L, and then all the cos and sine value. And you solve for the matrix again, you get negative. Negative means compression. Yeah, compression. So be careful on the axis again. Where is positive? Be careful on the angle. Again, angle is from the global axis X to your X prime, and the direction is anti-clockwise positive. Yeah. So these two is the fundamental or principle that you need to be careful when you solve problems. One single mistake on the angle, one single mistake on the axis, it will snowball, and at the end, your answer will be incorrect if you have the wrong understanding. Okay, the result you will see negative become positive, positive will become negative. So and some of the value will become very weird. Yeah? So when you get a negative for stress, it means it's a compressed stress. All right. So of course, in exam also expect that we ask you to explain. Do you get what kind of stress that stress that experienced by the element? Does it experience tensile or does it experience a compressed stress? Okay, so you need to know how to explain. Okay, a quick one. So if you have a symmetry structure, a textbook term is called reflective symmetry. So it means that you have the same side. If you mirror them, you can experience you can simplify your calculation. For example, the diagram that you see on the screen here. So let's say you have a truss system like this, and the length is the same. You see from point 2 to 4 is L, 4 to 3 is L, and then 1 to 4 is L, 4 to 5 is L, and although it looks very complex, and the stress and the force 2P is acting along 2 to 3. So you have 8 elements here, 1, 2, 3, 4, 5, 6, 7, 8. 8 element, and point 1 and point 5 is fixed point. So when you do analysis for this kind of structure, we only need to analyze half of the structure. Maybe I'll use red color. This is called symmetry structure, where if you mirror both sides, you will see the same thing. So we only need to analyze either side. You can choose left or right to analyze. Then you transfer into free body diagram like this. Only thing you need to be careful when you transfer is the force. The force will become half because you cut into half. And if you analyze and then you do analysis, when you arrive, you will still get the same answer for displacement and the stress inside the structure. Yeah. So only then you replace point number 4 with this constraint. It's a ball bearing constraint. If you press on point number 4, you can only move along vertical axis 2, 3. So that's why it was similar to a ball bearing constraint here. You will only move along vertical axis here. And then the rest will be the same because how we know it's 45? We know that it's 45 when we have the same length. In this case, you have the L both sides. So when you have a same length in trigonometry, you will get 45 degrees. All right. So this is how you solve for symmetry object. The procedure is still the same. And yeah, for point 2 and point 3 also same. You convert to a ball bearing a constraint where you can see that point number 2 will also move along vertical axis only. Right? Yeah. In this case, yeah, for this case, because there's only one force. If your force is this way, then you cannot use this one anymore. You put this way, then there's a displacement in the horizontal direction. So this is just an illustration how you solve for symmetry structure. Okay, so if you use ANSYS software to analyze, you can simplify into the one that on the right hand side. Okay, to save time also, and also to yeah, the main reason we can simplify is to save the calculation time. Okay. Yeah. So if you follow the same previous strategy to solve for displacement according to the boundary layer that we have here, you will arrive at all these equation. Yeah, this is just a illustration when you try to solve with the previous procedure that we learned. Yeah. Okay, with this we conclude chapter 3. Let me stop the recording.